See what we got for a light. My head might be cut off just a little bit. Do you have the remote?
Yes. Volume's good. Thank God.
All right.
Nobody's in the
Hmm?
Nobody's in the Zoom. Oh my gosh, do you expect people to?
It's off like 15 minutes early.
Oh, that's true. Do you think today we'll have a big turnout? I don't know. I feel like people want midterm review. Yeah.
Oh, they'll total. It seems like they would totally come. See what the hell I'm gonna say. I mean, at least have it listening in the. At least have it going in the background. Okay. Okay. So are we set? You can tune. We're ready to. You got volume. You got all we have to do is click go live.
It's live already.
All right. Can we pause it or do we have to just let it run?
We have to let it run.
Okay. We don't. Okay. All right. Okay. Good morning, everyone. Welcome to whatever it is, week 3 of Chem 1A exam day. So it doesn't look like the audience is particularly big this morning. So maybe there was some late night studiers. What we're going to do is review for the exam. We'll go through some. We'll do it chem quiz style. We'll go through chem quizzes that are representative of the questions you're going to see on the exam. We know pretty much what it looks like yet. We're actually going to tweak it just a little bit more today. We're trying to make it as fair as possible, but still have multiple versions. So it's taking some algorithmic work to make that work, but the student instructors and I am on it. So we'll hopefully have something good for you. Well, good in our estimation. I don't know what you'll feel about it by 6 p.m. Tonight when you're ready to go. So let's just start kind of back from where we started the class, and we talked about the amounts of stuff and how to keep track of amounts of stuff. So we talked about how measurements of stuff, so masses, volumes of gas, volumes of liquid, density, mass per unit volume, all those ways of keeping track of stuff we wanted to know about. We kept track of counting particles by using the definition of the mole, so Avogadro's number, and we had a long discussion of relative masses. So if your relative mass is 5 and someone else's relative mass is 10, those two relative masses have the same number of particles in them. That's how we defined relative mass, and we eventually defined that number of particles. Turns out the number isn't important. It could be any number. So the important thing is relative masses have the same number, whatever that number happens to be. We found it to be Avogadro's number, and that can be measured by various methods. And when you do go into the laboratory, one of the experiments you may do is, how to estimate or how to determine Avogadro's number. So we look specifically at the various circumstances you could have. So here's one of our favorite reactions. Hydrogen and oxygen reacting to form water. This is exothermic. This releases energy. This state, hydrogen and oxygen, are higher in energy than water molecules. So you have a high energy state goes to a low energy state. Energy leaves the system. It's exothermic. That energy leaves the system, and you can harness it in several ways. You could harness it as work. You can use some of the heat. It is an expansion, so there is an expansion because of the explosive and concussive nature of the event. So you can harness both work and heat from it. We're not going to try to divide them up. In this case, we're interested that energy leaves the system. So delta E is negative, it's exothermic. We can keep track of the number of molecules. So 2 molecules, 1 molecule goes to 2 molecules. And of course, you can multiply that by Avogadro's number. It could be 2 times 6.0 times 10 to the 23rd in each of those. The reaction of molecule to molecule is the same as the reaction of mole to mole, because a mole is just a number of molecules. So we show that right here. This number 2, that coefficient in the balanced chemical reaction, translates directly from molecules to moles, and that's what we expect it to do. If it were a gas, we found that gases, if they're all under the same conditions, have the same volume per mole. So a mole of gas and a volume of gas mean about the same thing. That is, this volume of gas H2, an equal volume of gas of O2 has the same number of particles. So here we've kind of done a 2-to-1. There's 2 times the volume of gas of O2, but the same number of particles. So we have, sorry, I said that. I said that wrong, didn't I? 2 times the volume of gas, twice the particles as this balloon. We found that we could relate moles, a number of particles, to relative mass. So the relative mass 2 to 32 here. So 2 grams of hydrogen has the same number of particles as 32 grams of oxygen molecules. We know that because those are the relative masses, 2 and 32. We can take the unit out, grams, it could be pounds. 2 pounds and 32 pounds of hydrogen have the same number of particles. The relative mass is the important part, not exactly what that mass unit is. But we found in for the case of mass, that is conserved. So the mass is conserved. There are the same number of grams, the same mass on either side of that equation. There's 36 grams of total mass over here. There's 36 grams of mass over there. Another thing that's conserved is the atoms themselves. We don't create or delete atoms. So there's 2 hydrogen atoms, or there's 4 hydrogen atoms here. There are 4 there. There are 2 oxygen atoms here. There are 2 oxygen atoms here. They rearrange, but we're going to conserve the atoms, and we're going to conserve the mass. And that just makes sense because atoms are where the mass is for these kind of expressions. So there are the relative masses. We talked about that a bit. We talked about isotopes and how the isotopes of atoms are flavors of atoms that have the same number of protons, but a different number of neutrons. So they have different mass, but they're the same element. The number of protons in the nucleus determines the identity of the element, period. If there are 6 protons in your nucleus, you are a carbon atom. I don't care what your mass is. You can have lots of neutrons. If you take nothing else home from Chem 1A, take home the fact that the number of protons in the nucleus determine the identity of the element. So carbon 14 is still carbon. It has mass 14, so you might think, oh, that's a nitrogen atom because that has mass 14 when it has 7 protons and 7 neutrons. But the mass does not help you determine the element, only the atomic number. Atomic number is the number of protons in the nucleus. So we have slightly different masses due to isotopic effects. So let's do some chem quizzes. We'll just do some, and I assembled chem quizzes that now that we know the exam looks like, we can do chem quizzes that focus on real stuff you're gonna encounter in the exam. So there's about 150 of us here in our Chem 1 class. I don't know how many are watching. Have we got up to more than 10? There weren't very many of you when we started. Oh, we're at 100. Welcome, hundreds of you. So there's around 100, let's say there's around 150. That's the enrollment, I think, something like that. So let's say 150 people pick an atom at random from 55 moles of carbon. I don't really remember why I put that in. Let's say you just have a naturally occurring hockey puck chunk of carbon. You'll realize the amount doesn't really matter. We're all going to pick, because we have magical tweezers, an atom of carbon. And then we're going to look at what we actually have in our pick. The relative abundances of the various isotopes of carbon are here. So carbon 12, carbon 13, carbon 14, those are all carbon. They're all present in the sample because it's naturally abundant sample. So there are these numbers of carbon isotopes. So let's talk about that amongst ourselves and decide which of these is the right number of people who will pick an atom with 7 neutrons. So into the breakout rooms, you can mute me, you can drop me. Are you ready to, can I go to your source? Okay. Okay, we're back. Ryan is ready to show us what you're thinking. So go ahead, Ryan. Wow, overwhelming, really, A already. As long as we're talking about percentages, it's 3 out of 4 of you think A. So 3 out of 4 people choose A or 1. Ooh, that's how tired I was last night. I didn't change those to A, B, C. Actually, maybe in your version there. Well, that'll be interesting to see. Let's see if when we go to my version, if they're A, B, and C. No, they are not. Okay, doesn't matter. The first one is the one you chose. I agree with you who chose the first one. The relative abundances. We here have, I was doing it for 500 people, but it doesn't matter how many people or how much carbon are there. The important part is there are 1 in 100 atoms of carbon that you pull out of nature. 1 in 100 of them is a carbon 13. So 1 in 100 people will get a carbon with 7 neutrons if everybody picks at random. And 1 in 100, there are about 100 of us or 150 of us. So about 1 of us will be the lucky 1 neutron winner. So the people who get carbon 14 going to be very rare. That natural abundance is very low. So virtually no one. We'd have to have tens of thousands of people picking before even 1 would get carbon 14. So 2 neutrons in there, or 2 extra neutrons in their atom for a total of 8 neutrons. Okay, so let's take it one step further. So here's sodium carbonate reacting with hydrochloric acid, forming sodium chloride, water, and carbon dioxide. How many moles of carbon dioxide will form from a reaction of 2 moles of everything? So I'm going to take 2 moles of everything. How many carbon dioxide moles will be formed? Think about that for a minute. We'll talk about it in our breakout rooms and see what we're thinking. Are we back? All right, we're back. I heard votes for A and B in my discussion group. We'll go to look at the poll here and see what you're thinking as a class. Same kind of thing, A's and B's. So let me give you my thinking on this one. I'll take back over the control of the board. Take back control. We have a Tesla S that we drive around. It drives, you may know, the Tesla S is a car. It has auto drive, so you can just let it drive. But you can take back over driving whenever you want. So I usually, and we named the car L, ELLE. That wasn't my idea. But I will just say, L, I'll take over. And I'll start driving again. So, Ryan, I'll take over. What were we thinking here? We have this chemical reaction, but it wasn't balanced. So, you have 2 moles of everything. And if you had 2 moles of everything, then you would get 2 moles here, 2 moles of here. You would get 2 moles of all of those. Absolutely. But it does have to be balanced. There's 2 required for the HCl. So that means 2 moles of HCl will react with 1 mole of sodium carbonate. So you react 1 mole of sodium carbonate, you use up your whole 2 moles of HCl. And then the reaction has to stop because there's no more HCl left. So you could look at it like this. Here are your first mole of sodium carbonate. It requires both the moles of hydrochloric acid that were there, and it would form the mole of carbon dioxide and 2 moles of sodium chloride. And the balls here now are moles. They're not atoms. Each represents a mole. But then you're done. So you've used up everything there. You still have your second mole, but no HCl to react with. So the reaction is limited by the HCl. When it runs out, we stop. So we stop after having produced just 1 mole of carbon dioxide. Okay. Let's do one more of these. Yeah, let's do one more. This is still in the same kind of topic, and we talked about other things. But this one is well, how about this? I will leave this. No, we'll go through it. I'm gonna say I would leave it for you guys to work out on your own. But of course, I've been a student too here at Cal. I did my PhD here at Cal, and there's nothing that you hate worse than an instructor saying, "Oh, I'll leave that one for you to work out on your own." Just say, "No, will you please just do it for us?" Let's all go through this one. This one will take us another minute or two than the other ones, I think. So I'm going to take a compound that has hydrogen, oxygen, carbon, and sulfur in it. And the mole ratios are 1 to 2 to 3 to 4. So I have a mole of hydrogen, 2 moles of oxygen, 3 moles of carbon, 4 moles of sulfur. What's the empirical formula? How does that mole ratio relate to the empirical formula? So is it 1, 2, 3, 4, 2, 3, 2, 6, or 1, 2, 1, 8? So empirical formula to mole ratios, let's talk about that one. You can mute me and drop me in a group. Are we back? Okay, so we're back, I think. Let's see what we're thinking as a group. Ryan will tell us. C, very popular. I thought I could kind of fool some of you to go mass to moles. These are the mass ratios. This has to be mole ratios or particle ratios. But I couldn't fool anybody. So excellent. I agree with you. And it was explained very well in the breakout group that I joined. It's funny, they had to explain it twice because I was trying to do the math as quickly as they were, and I couldn't. So I'll take back control. But yes, if you look at the ratios of their relative masses, you can convert those relative masses to numbers of particles, and the numbers of particles are what you want. So with those relative masses, you can see you've got 4 times the mass of sulfur, but you have compared to the hydrogen, you need 8 times that mass, or that mass will have 8 times the number of particles because this has such a low relative mass. So lots of mass, but low number of particles. Here, not as much mass, but high number of particles because of the lower relative mass. And you can just figure them out by the ratios. So 32 grams would be 1 mole of sulfur. If you had half as much, 16 grams, that'd be a mole of oxygen. If you have 3/4 as much, the carbon, that turns out to be 2 moles. And if you have 1/4 as much, 8 grams, that turns to be 8 moles of hydrogen. So well done, everybody. I don't think we'll be able to stump you on the exam if we didn't stump you there. This one we will skip. That's too much. So we talked about mass spectrometry. How do we actually get these relative masses? And putting the exam together, we ended up putting some mass spectra questions on there. I like them because a lot of things come together. You have to think about relative masses. You have to think about ratios. And you have to do it in a really the same way you would do in a laboratory. You would look at data and say, what are my relative masses? So we talked about how a mass spectrometer works. You have particles go through, ionize them, go through the magnetic field, and they are deflected. They're deflected relative to their mass. And I'm gonna just blast through the animations here. But you get a spectrum, a distribution of masses and amplitudes, and the amplitudes tell you something about the relative amounts. So a lot of O16 and maybe O16, O18, maybe less than 1/4 as many particles in that ratio. Here we have carbon 12 to carbon 13. We know now that ratio is, if it were naturally abundant, would be 1 to 100. So this peak would be quite a bit smaller here. So isotopic ratios are going to show up. The molecules can fragment. So sometimes you get the molecules blown apart by this process, and you have to account for the fragments. But if you know what you're putting in, or you can work backwards from what was in the reagents, you can say, oh, well, that's a legitimate fragment as well. Like maybe I got a CO instead of a mass at 44. I have a mass at 28 because I didn't have an oxygen flew off. So you can keep track of that in your mass spectra. So let's do a mass spectrum. We're going to take some reactants and make products. Which molecule, so which molecular formula, so we have a molecular formula of a molecule. These are the possibilities. I'm going to react by combustion. Here are the reactants. Then I take the products, I run them through a mass spec as well. Which of these molecules was in the reactant mixture? And remember, I do expect you to remember what combustion means. On the exam, sometimes we'll say reacts with oxygen, or we'll say combustion. Combustion means I react with oxygen. If it's a hydrocarbon, I react all the way to carbon dioxide and water. So think about that for a minute. I will join a group. Okay, we're back. This great chem quiz, all kinds of stuff to think about here. You probably had to think about every concept involved in stoichiometry and reactions. Let's see what Ryan has for the full group. B, a little bit more popular than A and C. I think I agree with the B's. I hope we did the math right in our section. So why do I think that's the case? I'll take back over the screen, and let's annotate here. Go to my annotate options. So in the reactants, there's a peak at 30 and a peak at 32. So in the reactant mixture, there's molecules of mass 30 and molecules of mass 32. The reaction mixture is one of these molecules and oxygen. It's a combustion. So one of these is probably oxygen. Oxygen has O2, has relative mass 32. It's 2 oxygen atoms, 16. So that is probably oxygen. That means that the reactant has relative mass 30. So that's already some information. If we look at the products, and these are all hydrocarbons, and we said whenever hydrocarbons burn in oxygen, you get carbon dioxide and water, and you probably recognize mass 44 as CO2 and mass 18 as H2O. This guy here, well, this is kind of real life. So if you had excess oxygen and you looked at the product mixture, that oxygen would still be there. So that can just be leftover oxygen. So I think what that tells us is we understand the peaks now. All we have to do is identify this one from the information we have. So the information we have is it has relative mass 30. So we can look at the relative masses. Here we have 18 and 12, that's 30. So this one is okay. And here we have 24 and 6, that's 30. And here we have same thing, we have CH2O there. So we have at least 30 plus 2 more hydrogens. So that one has mass 32. So that could have been in there, but it's more likely that this is oxygen and not that. But can't totally rule that out until you go a little further, I think, and say, actually, you could make arguments one way or the other. This ratio of water to carbon dioxide is something like 3 to 4 or something in that ratio. Here, when you form water, all the hydrogens from your hydrocarbon have to go into the waters. So you would say, well, I would have then 6, that would make 3 water molecules. The carbon dioxide, each one of those has to make 1 carbon dioxide. So 3 to 2 would be about right. That doesn't look like 3 to 2. Could work out for the others what that would look like. This one we're gonna cross out because we think that if that were the case, there would be this other molecule wouldn't have had any place. Both the molecules oxygen and that molecule would have mass 32. This mass is 30 would be something else. So it can't be this one. So we can look at our other option and say, well, here, that looks like 1-to-1 carbon dioxide to water. You can kind of read it off of there. So 1 carbon dioxide and 1 water would be formed there. So that is definitely not 1-to-1. And you have, you're left with B. So all kinds of chemistry in there, just keeping track of moles, keeping track of molar masses. That's a very good chem quiz. Work through that again if you didn't understand that, and that's going to help you a lot on the midterm. So we went on and we talked about absorption and emission and the two different kinds. We had continuous absorption and emission, and we also had discrete absorption and emission, individual lines. So individual photons we ended up being able to tell being absorbed or emitted. So you can have ranges of photons being emitted where you can't identify the exact wavelength, so you just see a general color. Or you might be able to identify the exact wavelength and identify the exact photon that you have. You could measure its energy, back calculate to the wavelength. You might be able to get a diffraction grating that's so precise you can read the wavelength right off your display and understand what that photon energy is. That's the more in some cases, that's the more common way. Certainly in the old days, the more common way to do it. Super duper fancy spectrometers now, you could grab the photon and analyze it. You don't care about that. They have fancy spectrum analyzers now that you can grab the exact energy and the exact frequency out. But that's the basic idea. We talked about the electromagnetic spectrum, and we talked about how the wavelength and frequency are related to the speed in an electromagnetic wave. Talked all about the properties of waves. So in general, wavelength times frequency is the speed of any wave, any transverse wave, so ocean waves, or waves moving along a string. And we talked about how different frequencies are in this entire radio spectrum, entire electromagnetic spectrum, from very short wavelengths, and these would be very high energy, high frequency, high energy. These are damaging radiation. It's called ionizing radiation, and I think you know why it's called ionizing radiation now. We've talked about how you can take electrons completely away from atoms and ionize them. So even ultraviolet is an ionizing radiation for many molecules. And ultraviolet light, you hear about that all the time. It's what you apply sunscreen so that ultraviolet radiation doesn't ionize the atoms and molecules in your skin. When you go to take x-rays at the doctor's office, you cover as much of your body as possible with the lead shielding or dense shielding. So the x-rays only go to one tiny part because they are ionizing. They're ionizing. So you want to restrict them to the smallest part of your body as possible. And in the very center, there's the visible region, then the microwave and the radio wave. And these radio waves had extremely long wavelengths. They can be wavelengths on the order of kilometers long. And those have very low energy. So those were able to broadcast through the atmosphere. We talked about amplitude a little as well. So here's high energy, low energy, and higher amplitude. Higher amplitude is this peak to peak height on the wave, or 0 to peak is fine to define the amplitude. So I could define the amplitude by that height. That height squared is a measure of the intensity, the energy per unit time that's coming through. And we eventually correlated that with the number of photons per unit time. So high intensity, higher photons per unit time. And of course, the visible region is just stuck right in there. And you should be very familiar with those wavelengths and colors. So there's a mnemonic. What is it that you do, the Roy G. Biv thing? This spells out a name: red, orange, yellow, green, blue, and then indigo is a color, and violet. Some people remember that by this name, Roy G. Biv. And you should try to remember the basic order of those and the approximate wavelengths. So let's do a chem quiz about absorption and emission spectroscopy. So I have 3 filters here, A, B, and C, and I've shown the filter's absorption spectrum. And I'm going to ask, if I have an orange solution and I look at it, I see that it's orange, I put these various filters in between. What color do I see after a filter is there? Which one will I still see an orange? So think about that for a minute and we'll take a vote. Okay, we're back. Let's see what the group is thinking. 103 of us now. A and C, popular. B, not very popular at all. I think I can see what you're thinking here. It's either going to be orange through here or here, one or the other. B is not going to be as popular for reason that's reasonable to think. C is about twice as popular as A. So let me give you my thinking on that. Oops, I don't have to do that. I'm just going to hit you again and go there. So it's got to be orange. After I after I look at it. So here's where an orange photon would show up. And if an orange photon shows up there, that means it would be absorbed by A. So A's absorption is strong in the orange region. B and C, neither of those absorb very well in orange. Orange has to fall. I guess I can look somewhat orange. Orange has to fall somewhere between the red and the yellow. That's your Roy G. Biv. So the orange is there. So I bet B would let the orange photons through as well. So I think if you said C, you were absolutely correct. But if you said B, I think you were also right. One of the things I do on exams, and it makes everybody angry, but I don't care, is that I do the mark all that apply. So you have to kind of consider every answer sometimes. So if you would have had to think very carefully, you'd say, oh, C is right, but I guess, shoot, I got to think about A and B as well. And you're going to encounter that on the exam, and you'll just curse me. I won't hear it. So please don't curse me when you see me later in person. So we can talk about discrete absorption and emission now as well. So we did continuous absorption and emission. So let's talk about the discrete case where it's individual photons. So here I have an energy level spectrum. It's you have the relative energies marked off here. So 4 times the energy from level 4 to level 1. This absorption occurs. Blue photon at 400 nanometers is absorbed, and a 600 is emitted. Those are both possible events. So which corresponds to the interaction with the 400 nanometer light? Let's talk about it. Okay, we're back. This one, a lot of discussion on this. So let's see what you're, shoot, it's the last button I want to push. Let's see what you're thinking. We'll ignore our active panel. I will get it out of the way. Yeah, and we are all over the range here. So let me talk through it. We do have, we know 400 will be absorbed and 600 will be emitted. So the ratio of those energies, we have the ratios of the energies of the levels because we've given the relative energies here. So you can read them off the plot. And for the exam, there are times where you're going to have to read, actually look at the intensities on the plot. So we have the ratio of their energies. The ratio of their energies goes like the ratio of their wavelengths. There's not very much information there. Sorry. Let me annotate. So the energies of the various photons are hc over lambda. So the ratio of their wavelength is inverse the ratio of their energies. So, but the ratio is the same there. We have the, to get to from 600 to a 400, we have to go 2/3 that wavelength. So we have that same relationship with the energy. Okay, that's this wavelength is 1.5 times the energy of this wavelength. So the ratio of the wavelength is the inverse ratio of the energies because of this. So the ratios of the energies tell you where I should be here then. I have a 1 to 1.5 ratio here, the 3 to 2, and the 1 to 2 has that 3 to 2 ratio in energy. So I can, if 1 to 3 is 400, then 2 to 1 would fit 600. So we're kind of predicting what's going on, and that's what you do in real spectroscopy. You see the lines that are being emitted, and you generate this spacing from them. So we talked about diffraction and interference, and might want to run the demo if I can. Let's see if it starts up. Here's an animation of diffraction and interference. And remember, there's two phenomena occurring. There's the diffraction, that is the spreading out, and that has to do with the uncertainty principle. That is, we're confining a distance, confining space in this direction. So we're getting a spread of momenta in the other, in that same direction. We're being less clear what our momentum is because we're being more clear about what our spacing, what our distance is. And that leads to just the diffraction. So this overall just spreading out rather than seeing an exact spot here that's exactly the size of our slit, it's a spread out slit. So we also have interference occurring, and the interference is the positive and or the high intensity and the low intensity spots that correspond to constructive and destructive interference on the screen. And we know that relates to the wavelength. And this animation is nice. It Melissa will have it posted for you, I'm sure, because she's good at that. So you can play with this, but here's wavelength 700 nanometers. I'm going to reduce the wavelength. So lower wavelength, higher energy, gone down to green light, and you can see as I do that, and I keep going down to bluish light, how the interference pattern is squeezing together. So I'm going to go to longer wavelength. The spacing spreads out on the screen, and we went through how that happens. And you can overlay the diffraction on top of that. And if you look at them, if you look at just the reaction of both of them, the diffraction gives you this drop off in intensities. The peak positions give you the wavelength. So we can do the animation where you're really looking at the experiment. So you look up the experiment and you see increasing the wavelength has that little intensity, that little distribution tighten up. So that's a brilliant animation. Oops, that's a brilliant animation. We also talked about how the intensity of the peaks was related to the probability of a photon striking in that position. And then we talked about the photoelectric effect, how electrons are ejected from metals based on the energy of the photon and not the intensity of the light. So you can put in very intense, very bright light. Very bright light just has more photons per second. Bright light, more photons per second. But if a single photon of that light won't knock out an electron, then 1,000 of them aren't going to knock it out either. It's a 1 photon to 1 electron interaction. So in order to knock out electrons, you don't go to higher intensity, you go to higher energy photons. And what you have to do is overcome the work function, which is the binding energy. And we know now we can associate this with ionization. We're pulling an electron off, photoionization. These are photoelectrons, we call them. And we can plot the kinetic energy of the electrons versus the photon energy or the frequency. So when we get past the minimum frequency or the minimum energy to eject an electron, the photon energies after that give you a higher kinetic energy of the electron. So you can barely knock it out, and it'll go a very slow electron, or very slow kinetic energy electron. More energy in your photon going up here knocks it out, and that additional energy goes to make it go faster. So it's literally collisions. Boom, makes it go fast. That's here, and pink, slow is down here, the energy of the photon. And you can do the calculation. You can subtract the work function from the energy of the photon to get the kinetic energy of the electron. And you see that's a linear plot. Y equals mx plus b. It's full on algebraic linear plot. You would guess that better be linear in the frequency. If you don't understand all that algebraic plotting stuff, you don't have to, but you do have to know that those plots are straight lines with that slope. And if you're really clever, that slope is Planck's constant, mx plus b. Okay. So let's put it all together again. Holy crap. Here I have an experiment where I'm bringing in my laser light. Oops. I'm bringing in my laser light here. The electrons coming off, I'm running through a diffraction grating and getting their measurement of their wavelength, because I'm looking at their wave-like properties. So the question is, there's green light. If I use blue light instead, what happens to this, the photoelectric diffraction pattern? So if you can do this, you are on top of the world. I love this one. Tell me everything. Go ahead. We'll go to our discussion groups. Are we live? We have to turn their volume down. I can still hear those guys. Okay. Okay, we're back, I believe, live. So let's see what you're thinking. A, super popular. C, B is not popular, unchanged. I think it's probably going to change. So it's either going to get a broader distribution, a increase in spacing or a decrease in spacing. So I had some very smart people in the group that I was in. In fact, they were saying, well, this is easy. What is he talking about? So, but they explained to me very well that if I have a blue photon now here coming in, and I don't know if I have a good animation here, I'm going to a shorter wavelength, so higher frequency. So higher frequency of photons, blue photons coming in. That shorter wavelength, but that wavelength is not going through this grating. The laser light's hitting the metal. It's the photoelectrons going through the grating. So actually, if you went to a shorter wavelength just of the light, we've already seen that would compress the pattern. But we're not looking at the change in the light. We're looking at the effect it has at the photoelectrons. But of course, as Olivia mentioned to me in the breakout group, of course, those we're talking about photons here. So if the frequency increases, that's higher energy photons. That gives you a greater kinetic energy electron. A greater kinetic energy electron has a shorter wavelength. So a higher frequency, higher energy, shorter wavelength, higher velocity. You can say my velocity increases, my kinetic energy increases. You can think about it as a particle, and then, well, particle to wave, and then say, okay, my wavelength actually goes down for the photoelectron as well. So the diffraction grating should also cause a tighter pattern. Amazing. We'll skip this one because it's the same thing. Actually, this one, yeah, go do this one on your own because it is a clever one. In fact, I wanted to somehow advance yet hide the answer from you. I can't do it because I can't skip ahead. But maybe if here's a way I could try to do it. I can go over here, not show you what's happening, go to here, and then go to there. Ha! So I did leave that one for you to work out on your own. Again, analyze the diagram, look at the energies, you can get through it. So we talked about quantum numbers and energies. Oh shoot, I think this isn't exactly the animation I wanted. But we talked about how if you take a wave-like property and you put boundaries on it, that causes the standing wave pattern that you see here. And this is the standing wave pattern for a particle trapped in a box. Particle in a box, we call it. How did we trap it in the box? Well, we didn't talk too much about this, but what we did is we said, we're going to take a region of space and we're going to say, in this region of space, L, we're going to say the potential energy is 0. Outside of that, the potential energy is infinity. So the particle can't go there because it can't get to infinite potential energy. So we trap it with these walls of infinite potential energy. That means all the energy of the particle is kinetic now. And these are the various expressions of that kinetic energy, low kinetic energy to high kinetic energy. The interesting thing, one of the most interesting things about trapped particles, quantum particles, is their lowest possible kinetic energy is not zero. So quantum particles, trapped, bound quantum states, you can't bring the particle to a stop. It's always moving a little bit. And we saw how that related to the uncertainty principle. So you can't stop it. If you could stop it, then you'd know the moment, you'd know the energy exactly. It would be stopped. M momentum, m times v, v is zero. You'd know the momentum is exactly zero. The uncertainty principle would say, well, then it's spread out all over space. When momentum is constrained, position is not. So you'd have to go to infinite size of the box, infinite space, if you know the momentum exactly. And that's actually kind of the case for photons. You know their momentum exactly, more or less, but you don't know where they are in space. They're somewhere on those waves, somewhere, but they're spread out who knows where when they're traveling freely, not bound. So that this is reinforced by this whole uncertainty principle. The uncertainty in the momentum times the uncertainty in the position is always bigger than about h, Planck's constant. So, oops, I'm going to annotate again. So this is a reflection of the fact that the uncertainty in the position and the uncertainty in the momentum, that's always bigger-ish, or the smallest it can be is around Planck's constant. The actual value over here, I'm not too concerned about, is all you know is that product has a value. So if one of these gets big, the other gets small. They're locked in this direct proportion. Okay, inverse direct proportion. So and we compared that to these energies to the electron in a atom, and now the potential field is different. Okay, so now we can go to high potential energies more easily because we can go towards the nucleus, and the low potential energies are pulling it apart. So essentially that inverts the scale. Zero in energy is up here instead of down here. And we drew those wave functions. The ground state, again, doesn't have zero energy. It has a negative energy, but it's big. The amount of energy is this much. We put a negative sign just to indicate it's less than zero. Okay, and we looked at the rest of the energies as a function of the quantum number n. And we saw ionizing is when you take a photon of greater than a Rydberg of energy to a hydrogen atom, and that would ionize. The electron would leave the system, leave the bound system, become free. And we talked about that a little bit in terms of the uncertainty principle. That's a beautiful argument as well. Don't worry about that for the exam. We'll come back to it a little bit after the exam. So we got the values of the Rydberg constant, the general relationship, n squared over r squared, n the charge of the nucleus. Actually, z, I just said all that wrong, I believe. Z squared over n squared with a minus sign indicating we're all less than zero. Z is the charge on the nucleus, n is the principal quantum number. So here we are, we're just thinking about it. Can a photon of 30 nanometer wavelength ionize helium plus from its ground state? Already taken one electron off, and if you've taken one electron off, it's a one electron system. So that just looks like a hydrogen-like system, one electron, one nucleus. The question is, can 30 nanometer photon ionize helium plus? So think about that. And we'll go into our groups and talk about that. Okay, bring me back. Are we back? Oops, I want to go to you there. All right, we're back. Let's see what you're thinking about that. About 100 of you voting, and yes and no. Yes and no are popular. That would make it seem like depends would be popular as well. So let's see. Oops, I can't do that. Let's see what. Let me share my thinking on this. So first thing we should realize is the figure I drew was for the hydrogen atom. I'm asking you to think about helium, but I drew hydrogen. So for hydrogen, Z is 1. Z is the atomic number, the number of protons in the nucleus, the number of charged particles. So it's Z equals 1. That's why this is minus a Rydberg, because the energy is going to go as a function of n, like, I'm going to write all the numbers out there, but it's going to go like Z squared over N squared times the Rydberg constant. So that's why this is minus R for the ground state of hydrogen, because Z is 1 and N is 1. When you go to helium, Z is still the atomic number, the number of protons in the nucleus. So Z is 2, but N is still 1. We still got to ionize it from the ground state. So for the ground state of helium, it's 2 squared R. So this is minus 4 R. That's like way down here off the screen, low for the ground state of helium. So what you had to think about yourself is, well, this distance here from 1 to 2 in hydrogen, that's about 3/4 of a Rydberg in energy. You're going from minus R to minus 1/4 R. That's 3/4 of a Rydberg. So that corresponds roughly to 120 nanometer wavelength. You're got to say to yourself then, well, if I go down to minus 4 Rydbergs and I want to ionize, is 30, I've gone to shorter wavelength, so I've gone to higher energy, is 30 nanometers sufficient? So I probably have some animation there. Yep. 3/4 R is that energy gap. So 30 nanometer wavelength is that 4 times 1/4 Rydberg, and that is it 3R? Because I have to get a total of 4R, and that's not enough. So 30 nanometers would correspond to about 3 Rydbergs. I need 4 Rydbergs. I can't quite get there with 30 nanometers. Goodness gracious, that was tough. Are you tuned? Oh, yeah. How do we mic you? Stand really close to me. Okay, so we'll take a break. Ryan, one of your student instructors, she had chemistry a couple years ago, Chem 1, that's where we met. Actually, we met, Ryan and I, because I was in chemistry lecture. I wasn't giving the lecture. My colleague Phil Geisler was giving the lecture, but I was going to lecture, was part of the teaching team. And when I sit in the lecture hall, I do what I do here. I talk to people around me. Ryan was one of those people around me, and she was so impressive that we ended up working together later. And I say that because she's in the room.
I think we were so lost.
So Ryan has, when Ryan was taking the chemistry course, first exam, she wrote a song summarizing her feelings about Chem 1. We'll share that with you. And then if you want to hang around a few minutes afterwards, we'll maybe do one more chem quiz. But we really covered a lot of the stuff you need to know. So Ryan, you want to use your chair? So you can bring your chair. I'll get out of the way, but I'll stand relatively closely. Sure, I'll put the lyrics up while you get your guitar. Ryan has the lyrics of the tune, or lyrics of the song. I'll make them bigger. This goes to the. Oh, I can't. Why can't I stretch? I thought I could stretch the screen no matter what.
Well, that's because it's that.
Yeah, but I thought I could. That doesn't matter. This.
When it's the most zoomed out that it is.
Okay, so we have lyrics of the song. You'll recognize the tune. Jason Mraz, I think.
Yes.
Go ahead. I'll stand close so my mic picks up everything happening.
This is just a sec, 'cause I'll be giving it my best. This society of my chemistry will have a jam session. The word on earth is our record. I'll explain it all first. So I take the test Tuesday. Today. Sorry, the original test was Tuesday. You're gonna do great on midterm. Scrolling perpetually. Sorry. So open up your notes and sing with me. See if you can wavelength my frequency. Remember that along wavelength means low energy. Listen to me when I say that L is superorbital D. Lots of notes means higher E. And it's our God-forsaken right to pass this midterm. So I won't answer. I take the test Tuesday. You're gonna do great. There's no need to hesitate. Full shells aren't ground safe. Oh, that one's something you don't know. Don't worry about that. We're gonna do great on midterms. Do you want to do well? Read a little closer. There's a reason to fear. I've been spending way too long on systems and their surroundings where energy goes in and out and work as heat. Work as heat. You did it all in class. Check the signs so you can pass. I guess what I'll be saying is we know relative classes, comparing all the ratios of multiple gases with useful ratios to compare. And we balance our reactions. Do that on the test. It's really important. You're going to get it wrong if you don't balance your reactions. So
the test today. Today.
You're gonna do open up
your notes and sing with me. My test you can see is delta E. Electrons in a higher N have low stability. Please don't, please don't, please don't.
There's no need
to complicate. Time is short.
You are gonna do great on midterm.
Woohoo! Yay!
Thanks for clapping. I was really scared that I was just going to call it after because nobody's in the room. Yeah.
Thank you.
Go back to my voice, Bill.
Well, it's excellent because it is so topical and lyrical and fun. Parody songs, the spice of life. Let's go. I just want to see if there, you guys, you stay or go. I'm just going to see if there's anything else. I don't think there might just be. Yeah, the last thing we talked about are wave functions and their various quantum numbers. So we were able to do the three-dimensional quantum system, and we did the three-dimensional quantum system. We had three quantum numbers. And each of those quantum numbers, each set, N, L, and M sub L, corresponded to a property of the wave function. And we were able to delineate those and the relationships between them. So you can do this one on your own. I'll leave you thinking about this, something like you'll see on the exam. Here's a drawing sketch of an orbital going from positive amplitude to negative amplitude to positive amplitude of the wave function. We square that to get the probability distribution. What are a good representation of the quantum numbers, NL and M sub L, given that distribution there? So if you can do all those things, I think you'll be ready for the midterm this evening. Good luck. we're going to go all take it ourselves right now, actually, and make sure it's not too long. So good luck. We'll see you all tomorrow. Wait, something very important. Tomorrow, the first chem quiz will be the question on the midterm that is most frequently missed. And if you get it right on your chem quiz tomorrow in class, we're going to give you the point back. If you missed it, we're just going to give you a point if you get it right. So you can get your point back if you were one of those who missed it. Spread the word on that. I don't know. Do we still have 100 people in the? We still have lots of viewers, so most of you have heard that. I'll try to remember to send it out in an announcement. That's just a fun way to just do a callback to the midterm tomorrow's lecture. Okay, see you then, guys.